Hello students, myself Aritraj Chakraborty. Today we are going to discuss the three-phase induction motor. At first, the classification of induction motor. So according to the rotor construction, induction motor can be classified into two categories. Number one, squirrel cage induction motor, or the induction motor consists of cage rotor, and number two, the slip ring induction motor or wound rotor induction motor. And depending on the number of phases, it can be classified as single phase induction motor and three phase induction motor. Now the construction of induction motor. A three phase induction motor consists of two major parts. Number one, the static part, that is the stationary stator, and number two, the rotating part, that is the rotor. And here the constructional features of three-phase induction motor shown below. There is a motor frame or yoke. Inside the yoke, the standstill stator and rotating rotor is installed. Two numbers of fan blades are attached with the shaft of the rotor for cooling purpose, and there is a wiring cover in which the stator terminals are connected, and the stator terminals are connected with the three-phase AC source, and the end belts are attached with the motor frame or yoke. The next part is the stationary stator. The stator is a stationary part, is built up of high-grade alloy steel lamination to reduce the eddy current loss. The laminations are slotted. The inner periphery and the outer periphery are insulated from each other, and the insulated stator conductor are placed in this slot. The stator conductors are connected to form a three-phase winding. It may be star connected or delta connected winding. Now the next part is the rotating part, that is the rotor. The rotor is also built up of thin lamination of the same material where the stator is made. The laminated cylindrical core is mounted directly on the shaft or a spider carried by the shaft, and these laminations are slotted on their outer periphery to receive the rotor conductor. There are two types of induction motor rotors. Number one, a squirrel cage rotor, and number two, the wound rotor or slip ring rotor. At first, the squirrel cage type rotor. Rotor winding is composed of copper bars embedded in the rotor slot and shorted at both ends by end rings. It is simple, it is low cost, it is robust, and it requires low maintenance. It consists of a cylindrical laminated core with slots nearly parallel to the shaft axis or skewed. Each slot contains an uninsulated bar conductor of aluminum or copper. At each end of the rotor bar conductors are short-circuited by heavy end rings of the same material. The conductors and the end rings form a cage of the tire, which was once commonly used for keeping the squirrels. Hence its name, a cage rotor. which is shown below. Now, the wound rotor. Rotor winding is wound by wires, and the winding terminals can be connected to external circuit through slip rings and brushes. Easy to control speed, and it is more expensive. The wound rotor consists of a slotted armature. Insulated conductors are put in the slots and connected to form a three-phase double-layer distributed winding similar to the stator winding. The rotor windings are connected in star. The open ends of the star circuit are brought outside the rotor and connected to three insulated slip rings. The slip rings are mounted on the shaft which connected to the short circuit gear. The purpose of slip rings is to provide a means for connecting the external resistance by the help of brushes in the rotor circuit. Now, the principle of operation. When a three-phase stator winding is connected to a three-phase balanced voltage supply, a three-phase balanced current will flow through the winding. The magnitude of this current are same in each of the phase, which also will induce three-phase flux in the stator, and the electrical angle between these three flux are 120 degree. This flux will rotate at a speed called a synchronous speed, denoted by small ns, and this small ns is known as the synchronous speed in RPS, and the flux is called as rotating magnetic field. The synchronous speed is given by the expression, that is ns equals to 120 f by p. Here p is the number of poles and f is the frequency of the supply. Now, the rotating magnetic field cuts the rotor winding and produces an induced voltage in the rotor windings. When the rotor is at standstill mode, the rotor conductors cut the rotating magnetic fields, and according to the Faraday's laws of electromagnetic induction, an induced EMF is produced in the rotor windings. Due to the fact that the rotor windings are short-circuited for both squirrel cage and wound rotor, an induced current flows in the rotor windings, and the rotor current produces another magnetic field, and a torque is produced as a result of the interaction of those two magnetic fields. Now, the next topic is the slip. The rotor speed of an induction machine is different from the speed of rotating magnetic field. The percentage difference of the speed is called slip. That means percentage slip equals to ns minus n by ns into 100. Ns is the synchronous speed in rpm, n is the rotor speed in rpm. When the rotor runs at synchronous speed or nearly equal to the synchronous speed, then the rotor speed is ns or nearly equal to the ns. At that time the slip is equals to 0, and if the rotor is in stationary condition or is in standstill mode, then the rotor speed is 0. At that time the slip is equals to 1. Now, the effect of the slip on rotor frequency, that is Fr equals to the multiplication of slip and the supply frequency, where Fr is the rotor frequency, and effect of the slip on rotor induced EMF, that is ER2 equals to SE2. S is the slip and E2 is the standstill induced EMF of rotor, and ER2 is the rotor EMF. And effect of slip on rotor resistance, reactance and impedance, that is R2 equals to RR2. Actually the resistance is constant for standstill mode as well as for the running mode, and the XR2 equals to S into X2. X2 is the standstill inductive reactance of induction motor, of the rotor of the induction motor, and the Z2 equals to root over R2 square plus SX2 square. Here R2X2 and Z2 is the rotor resistance and reactance and impedance respectively at standstill condition, and F is the supply frequency and E2 is the standstill EMF. Now the next part is the torque slip characteristics. When S equals to 0, that means when the rotor speed is equal to the synchronous speed. Actually the rotor speed is nearly equal to the synchronous speed. Under this condition the motor stops, so the torque T at this value S equals to 0. Okay, this shows that the torque slip characteristic starts from the origin. Now for smaller value of slip, the torque is directly proportional to the slip, and for larger value of slip or at high slip region, the torque is inversely proportional to the slip. So this is the torque slip characteristics graph. At x-axis the slip, and at the torque is at the y-axis. When S is nearly equal to the 0, at that time the motor is running at nearly to the synchronous speed. The torque is gradually increased, or torque is proportional to the slip. At medium slip region or at S underscore region, the maximum torque is occurred, or the peak torque or the peak value of torque is reached. And at slip 1, or when the motor is standstill mode, or if we connected a full load to the motor, or if we block the rotor, then the slip is 1 because the rotor speed is 0. At that time the torque is gradually reduced. So this characteristics is like a hyperbola. Now the ratio between starting torque and maximum torque, that is TST by Tmax equals to 2 Sm by S square m plus 1, where TST is the starting torque and Tmax is the maximum torque. Sm is the slip at maximum torque. Now the equivalent circuit of induction motor. So this is the equivalent circuit at open circuit condition. Just like a transformer, there is a primary side, this is the stator side, and there is a secondary side, that is the rotor side. R1 is the primary resistance, X1 is the primary reactance, R0 is the core resistance, and X0 is the core reactance. Here is the core, is the air core. E1 is the primary induced EMF and E2 is the secondary induced EMF. R2 is the secondary resistance and X2 is the secondary reactance at no load condition or at open circuit condition. Now the equivalent circuit of induction motor at short circuit condition. When it is short circuit, it means when it is in running condition, then a slip has come, so the E1 is the primary induced EMF and SE2 is the secondary induced EMF, because it is the slip has come at running condition when the copper bar are short circuited. R2 is the secondary resistance, R1 is the primary resistance, same as X1 is the primary reactance and X2 is the secondary reactance, and R0 or X0 are respectively the core resistance and core reactance. And this figure or this equivalent circuit shows the equivalent circuit with electrical equivalent of mechanical load. When a variable resistance is connected at rotor, it means in case of slip ring induction motor where the copper bar is connected to the short circuit gear by the help of slip ring. Now the no load test or the open circuit test. Here we can see the delta connected stator, which is connected to a three-phase supply, and the three numbers of ammeters are connected with each phase, which are measuring the line current, and the voltmeter, which is measuring the line voltage. In case of delta connection, the line voltage equals to phase voltage, and there are two wattmeters which is measuring the total wattage of the supply. This test is similar to the open circuit test on a transformer. The motor is uncoupled from its load, and the rated voltage at the rated frequency is applied to the stator to run the motor without load. The input power is measured by the 2 wattmeter method. An ammeter and a voltmeter are connected as shown in the figure. The ammeter measures the no load current and the voltmeter gives the normal rated supply voltage. Since the no load current is 20 to 30% of the full load current, and the I square R loss in the primary may be neglected as they vary with the square of the current. Since the motor is running at no load, total input power is equal to constant iron loss, friction and windage loss of the motor. Since the power factor of the induction motor under no load condition is generally less than 0.5, 1 wattmeter will show negative reading. It is therefore necessary to reverse the direction of current coil terminals to take the readings. Now the no load test parameters. The motor is allowed to run freely, and this test determines the rotational and core loss of the motor from the following relation. Here cos phi is the power factor, P0 is the power input to the motor, and This V0 is the input voltage, or I0 is the no load current, and the IW is the working component of the current, and which is equals to the I0 cos phi 0, and I mu or Im is the magnetizing component of the current, which is I0 sin phi 0, and R0 or the core resistance equals to V0 by IW, and X0 equals to V0 by Im. This R0 is responsible for eddy current loss, and X0 is responsible for hysteresis loss. So by the using open circuit test, we can measure the no load parameters. Now the next part is the block rotor test or short circuit test. This test is analogous to the short circuit test of a transformer. In this test, the shaft of the motor is clamped so that it cannot move, and rotor winding is short circuited in a slip ring motor. The rotor winding is short circuited through slip ring in cage motor. The rotor bars are permanently short circuited. This test is also called the locked rotor test, and the circuit diagram is shown below. A reduced voltage at reduced frequency is applied to the stator through a three-phase autotransformer so that the full load rated current flows in the stator. The following three readings are obtained. In the wattmeter, the total power on short circuit, that is the algebraic sum of two wattmeter readings. In the ammeter, the line current or short circuit, and in the voltmeter, the line voltage on short circuit. And here the block rotor test parameters. In this test, the rotor is blocked from rotating by connecting load with belt mechanism. This test gives the total winding resistance and leakage reactance of the motor, that is cos phi s equals to Ps by root 3 Vs into Is. Vs is the short circuit voltage, Is is the short circuit current, and Ps is the total power input on short circuit. R equivalent equals to Ps by 3 into Is square, and Zeq equals to Vs by Is, and equivalent reactance equals to root over of equivalent impedance square minus equivalent resistance square. Now the starting of three-phase induction motor. There are three methods of starting of squirrel induction motor which are shown below. Number 1, direct online starter or direct online starting. Number 2, auto transformer starting, and number 3, the start delta starting. Number 1, the direct online starter. This is the circuit diagram of direct online starter. In the derailleur starter, the method of starting cage motors, the motor is connected by means of starter across the full supply voltage. It consists of a coil operated contactor controlled by start and stop push buttons, which may be installed at convenient places remote from the starter. On press the start push button, The conductor coil is energized from two line conductors, that is the R and Y, or R and B, or Y and B. The three main contacts and the auxiliary contacts are, and the terminals are short circuited. The motor is thus connected to the supply. When the start switch is released, it moves back under spring action. Even then, the contactor remain energized, the main contact are closed, and the motor continue to get supply. For this reason, it is known as hold on contact. When the stop switch is pressed, the supply through the contactor coil is disconnected. Since the contactor coil is de-energized, the main contacts and auxiliary contacts are opened, the supply to the motor is disconnected, and the motor is stopped. Next, the auto transformer starter. An auto transformer starter is suitable for both star and delta connected motors. In this method, the starting current is limited by using a three-phase auto transformer to reduce the initial stator applied voltage. The auto transformer is provided with a number of tappings. In practice, the starter is connected to one particular tapping to obtain the most suitable starting voltage. A double through switch is used to connect the auto transformer in the circuit for starting. The start position, the primary of the auto transformer is connected to the supply line, and the motor is connected to the secondary of the auto transformer. And when the motor picks up the speed, say about 80% of the rated value, the handle of double through switch is quickly moved to the run position, and the auto transformer gets its full rated voltage. The handle is held in the run position by the under voltage relay. In case of the supply voltage failure below a certain value, the handle is released and returned to the off position. And of course, the overload protection is provided by thermal overload relay. Now, the next is the star delta starter. This is a very common type starter and extensively used compared to the other type of starter. A star delta starter is used for a cage motor designed to run normally on delta connected stator winding. When the switch is in the start position, the stator windings are connected in star, and when the motor picks up speed, say 80% of its rated value, the changeover switch is thrown quickly to the run position, and which connects the stator winding in delta. By connecting the stator winding first star and then in delta, the line current drawn by the motor at starting is reduced to 1/3 as compared to the starting current with the windings connected in delta. At the time of starting, when the stator windings are star connected, each stator phase gets a voltage, that is VL by root 3. That means line voltage by root 3, where VL is the line voltage, and since the torque developed by an induction motor is proportional to the square of the applied voltage. Star delta starting reduces the starting torque to 1/3 that obtainable by delta delta starting. Next, the speed control of induction motor. The speed control of squirrel induction motor can be controlled by following methods. Number 1, the variable voltage and variable frequency method of controlling the speed of induction motor. Number 2, the speed control by changing the supply voltage. And number 3, the speed control by changing the number of poles. All these three methods are applied in squirrel cage induction motor. And also the speed control by changing the rheostat connected with the stator terminals. This method doesn't apply very much. And the speed of slip ring induction motor can be controlled by following method. The speed control by changing the rheostat or short circuit gear connected with the rotor terminals. That means the rotor, by controlling the rotor resistance, the speed control of slip ring induction motor is done. Now the braking of induction motor. The braking methods of induction motors are as follows. Number 1, the regenerative braking. When a motor driven any locomotives comes from an upper region to a lower region by a slanted way, this motor is converted into induction generator. At that time, it supplies the power to the line. When this motor is running to the lower region to upper region, at that time it collects the power from the power lines or from the supply, and when the reverse is take place, at that time the motor is converted into generator and it supply the power to the source. That means it is converted into induction generator. This type of braking is called regenerative braking. Number 2, plugging. This plugging is nothing but the plug changing. If the phase sequence of a stator winding is changed, then the direction of rotating magnetic field is also changed, and at that time the motor is stopped. This is known as plugging. And at last, the dynamic or rheostatic braking. When there is a variable resistance is connected in the stator terminal, and by controlling the resistance, the flow of current to the stator is controlled and the speed of the induction motor can be controlled by this mechanism. Okay, that's all. Thank you.